Good morning. Happy Tuesday to you. At least, I hope you're watching this on Tuesday, because if you're not watching it on Tuesday, that means you're probably a little behind. But that's okay, because I've given you not one, not three, but two days to complete the assignment. I'm going to introduce the Pythagorean Theorem to you, and I'm going to send you a Google form. Well, I'm actually going to send you a paper that has a bunch of problems on it, and you're going to work the problems on the paper and go through the Google form, select the right answer. The Pythagorean Theorem is a great theorem, so named after Pythagoras, though the ancient Babylonians and the Sumerians, they knew about the Pythagorean Theorem long before Pythagoras came around and put his name to it. I guess maybe he didn't put his name to it. I don't know. I don't think so. Maybe. Who knows? The Pythagoreans were some crazy people. If you want to read into their some of their historical math achievements, they're pretty interesting people. Anywho, a right triangle. So we cannot use the Pythagorean theorem unless we have a right triangle. And this is assignment A6, I believe. Yep, A6. Pythagorean theorem, we have a right triangle. The side opposite the right angle is always the hypotenuse. The other sides we call the legs. Okay, usually when they do the Pythagorean theorem, they label the legs A and B and the hypotenuse C. I'm using lowercase a's, b's, and c's, remember. And the theorem goes like this. The sum of the squares of the measures of the legs is equal to the square of the measure of the hypotenuse. The sum of the squares of the measures of the legs. Sums, we're adding something together. What are we adding? We're adding squares of the measures of the legs. The sums of the squares of the measures of the legs of a right triangle is always equal to the square of the length of the hypotenuse. That's the Pythagorean theorem. Really nice, really handy. Here's the first example. And what we really have to pay attention to is what is it we are looking for here, right? In this one, we want the hypotenuse. So C, and I said C squared, but I did not square it. C is our x here. Our legs are 6 and 15. Hypotenuse, always opposite the right angle. So we have that 6 squared plus 15 squared is equal to x squared. Okay? And that means then that x, we're going to take the square root of both sides. And then x is equal to the square root of 6 squared plus 15 squared. The 6 squared plus 15 squared, if you enter it into your calculating device, I believe is 261. Excuse me, not 261, 261. Okay? And remember that we like to simplify our square roots. And so we find some perfect squares that are factors there, and we see, oh, 9 factors 261, it goes into it 9 times. That is 261 is the same as 9 times 29. Remember that a square root of a product is a product of square roots. Square root of 9 is 3, and there are no perfect squares that divide square root of 29, so we have 3 square roots of 29 for example 1. Notice in that problem we were finding what? The hypotenuse. Look at example 2. The number one thing people do wrong with these types of there's a couple things I want to show you. But the first thing that I was going to mention is that they will set, most people, the first time you do a couple of these, you're going to set it up as 36 squared plus 39 squared is equal to x squared. That's what we did in the last problem. Well, guess what though? Here we have the x as a leg. And the other thing that people do is notice that they always want to do stuff like this. oh, 3 squared plus 4 squared. And then they raise their hand and they say, hey, Mr. Power, I have a great question for you. And I say, what's your question? And they say, is the square root of 3 squared plus 4 squared, is that the same as 3 plus 4? And I'll say, I don't know, find out. And maybe on this side we'll say, what is 3 squared? 9 plus 4 squared. 9 plus 16 is 25. Oh, no, that's not, huh? So you cannot do that. That is called the something clause, so named after a student that graduated last year. I'm not going to tell you who he is. Anyways, sum of the squares of the measures of the legs. X squared plus 36 squared is equal to 39 squared. That means that x squared is equal to 39 squared minus 36 squared. We take the square root of both sides, and then x is equal to the square root of 39 squared minus 36 squared. And here I'm telling you that this is not equal to 39 minus 36, but guess what? Some of you are going to do it anyways. I don't know why this is. You tell somebody to not do something and they just want to do it. I wonder if people watch the videos. Anyways, though, let's see. Where is my paper? It is lost in the abyss somewhere. Ah, this one works out nice. And 39 squared minus 36 squared happens to be 225, which happens to be a perfect square, and x is equal to 15. This one, you look at this and you say, oh gosh, this is terrible. I don't want to do this. Why are you making us do this, Mr. Power? This is one of these questions that you guys get really, really mad at because the answer works out really nice. So first off, make sure what you have here. The hypotenuse is right here. So we are not solving for the hypotenuse, we are solving for a leg. So we have x squared plus 3/4 squared is equal to the square root of 27/4 squared. And before you freak out, I'm just going to remind you something. This is just 3/4 times 3/4. We multiply fractions straight across the top, straight across the bottom. So this is 9/16. On the right side here, we have the square root of 27 over 4 times the square root of 27 over 4. On the top, remember that a product of square roots can be written as a square root of product. So this is the square root of 27 squared over 16. Square root of 27 squared, that's a doozy. You might have to get your calculator. But the square root of 27 squared, I heard it, good, is 27. Okay? Subtract 9/16 from each side, and we have 27/16. Take away 9 of them, leaving 16 of them. Oh, goodness. X squared is equal to 1, and we take the square root of each side, and x is equal to 1. You didn't like that one, did you? Told you, it wasn't so bad. Just like most things. Pythagorean triples. Pythagorean triples are numbers A, B, and C. These are the triples that I'm talking about. These guys right here, they are Pythagorean triples if they are positive integers and they satisfy the Pythagorean theorem. So 3, 4, 5 is a classic Pythagorean triple. Carpenters use it a lot. You can see these little 3, 4, 5 little squares if you look in your father's tools, perhaps. I dilated this one by multiplying the sides by 2. Remember that if I multiply each of these by 2, these side lengths are going to be in proportional relationships, so they are similar, hence the same shape. Right? So 10, 8, 6 is another Pythagorean triple. You could see that you could generate more of them. Right? The next one, if you wanted to multiply by 3, would be 15 on the hypotenuse, 9 on this leg, and 12 on this leg. Okay, so you can generate an infinite amount of Pythagorean triples given 1. The lowest one, where these guys are all co-prime, they're relatively co-prime, they don't have any numbers that divide them. These are called Pythagorean primitives. They are primitive Pythagorean triples. Here are 3 more primitive Pythagorean triples, 5, 12, 15. 8, 15, 17, 24, 7, 25. All of these satisfy the Pythagorean theorem, and they are positive integers, so they are Pythagorean triples. Okay? Good luck with this. Have fun. Work hard. You don't need luck, really. All you need is a little bit of perseverance, a little bit of willingness to ask for help when you get stuck, and, well, that's pretty much all you need. So, I love you. I miss you. Reach out to me if you need me.